Back, in the last video I started finite state machine, and we are looking into a particular example. I explained the example, what is the task for us in the last video, so I'm not going to repeat that. Please watch last video and you will get that clear. Okay, so what we do is, as I said, oops, not that one, we are going to create this controller. Bringing our state machine general diagram, and to explain you with these signals in mind. Okay, this is our flip-flop. We will see how many bits we need for them, but let's call next state S prime. I'm using the same terminology that book used, and last time I explained which book I've used for this example. And current state is S. We have combinational circuit. Since it's more state machine, there is no input going to determine the actions from here. Actions only depend on current state. Actions are lighting A, uh, traffic light, traffic light B. Okay, this is A, and this and east west are B. And we have sensor A, sensor B. Sensor A is north south, sensor B is east west. That is clear. Just replace proper signals or the outputs that we have. Okay, so what we do here right now is, here is the fun thing. Where should I start? Okay, let's look into this first. Maybe it's better if you don't look into this. Or maybe it's better if I move this away from you, because it's hard not to look at it. Okay, that's good. All right. I should bring this example here. Can delete it later on. Okay, let's copy this. Bring here, make it smaller. All right, I think that's good now. So when reset happens, RT I call it, but here I'm writing reset. When reset happens, we are in S0, state 0. And what happens in state 0? Our light A, I should mention it here. This is A north south, and this is B east west. Okay, what we do is, the A traffic light is green, so this and this are green, so traffic is going from here, and these are off, and that is the default, says we are giving priority in the beginning to these guys. Now TA, and we stay in this one if this sensor here and here are 1, means they are sensing people here. As long as people are here, we are keeping this street on. So T is 1, and that is the input. We stay here. Now while we are here, when TA is 0, there are no students on this side, we go to another state for 5 seconds. Clock is 5 seconds. What we do is, we make this yellow, and this is still red. Okay, we are just turning this yellow, as you understand how traffic light works. Then after staying in this for 1 clock cycle, we're not checking anything. You see that there's no signal here. All we do is, staying in 1 cycle, exactly move to a state 2. What happens in state 2? We turning this one red, and now these are B is on. B stay, we keep staying in the state S2 as long as there are this sensor, these two are on. Means there are people here. Now, as long as there are people here, the students here, we keep this on, and when it's not, we go to another state for just one clock cycle. And in that case, now we put this one in yellow and we put this one into still red because we are in a transition state. Then we go without checking anything after one cycle, go back to S0. Now this is off and this is on. So state machine give you this nice sequence of things, and we change from one state to state on the rise edge of the clock, and only once these inputs are 1 or whatever, 0 in this case. Understood? I believe that is simple. Okay, now question is how you gonna implement this one. And here comes, I think now is the time I move this guy out. Okay, bring this thing back. Over here because I want to put them side by side. Let's look at, we are in S0. So this table is going to say the same thing that you see in diagram, but it's more in the tabular form. And this is good for us because based on this we will create our Boolean equations. So we need a truth table. Going back to combinational circuits. So we are in S0, let's say here. This is current state. And if you remember, we call current state S, which is a flop output. We have to determine next state, we call S prime. And we do that based on our next state. This one. Changes based on inputs and based on current state. Are you with me? Yeah, here we go. Let's bring this picture here instead of me going back and forth. Let's bring it here. Okay. So now we've already gone through this. We're looking into this, but using this and this. Our current state, when we are in S0, this thing is S0. As long as t is 1, we stay in S0. So S0, as long as t is 1, doesn't matter what the TB is, we stay in S0. So we are determining this S prime, future current state. Based on what? Based on current state and based on inputs. And here we said, if this one is S0, if this one is S0 and we have TA1, so this combinational circuit is deciding that. Deciding if this is S0 and T is 1, this needs to be S0 so that on the next rise edge of the clock, this stays at S0. Understood? If this thing is S0, this thing is deciding, and TA is 0, this thing is 0. We are, what binary value we are bringing here? That corresponding to S1. We need to move to, when T is 0, we move to S1. We need to put S1 here. When the next rise edge of the clock comes, it sees this, it moves it to the output without any problem. So the next rise edge of the clock, next current state, I keep mixing myself. So our current state is S0 and T is 0, and next state here becomes S1. So we are here. So right now we are just doing this part. Okay, let's cover this one over here. Sorry, going back, and maybe want to cover this part too so that we can move to the next page together. Okay, so that is When this one is S1, it's simple. Doesn't matter what TATB are, we will go to the next state S2. When we are in S2, there is two possibilities. TB is 1, TB is 0. When we are at S2, when TB is 1, we stay at S2, and when current state at S2, TB is 0, move to S3. When we are S3, it doesn't matter what TATB, we go to S0. So basically we have explained this now by using 0 and 1s for T and B. And these things you already know. Okay, these ones are outputs, LA, LB. This is this. So S0 means LA is green, LB is red. You see that? S1, LA is yellow. I mean, I put orange here so that way you can see it properly. Orange, red, orange, red. S2, red, green, red, green, red, green. S3, red, yellow, red, yellow. Now you must be wondering that, okay, Rashid, how we explain S0, S2, S3, and these red, greens in digital? I mean, everything eventually in our circuit has to be 0 or 1. Now I'm still using, for better explanation, these word S and just the signal there. So in next video, yeah, we have to do yet another video. In next video, I'm going to explain, I will go to the next stage of implementing this state machine, and that's where you will see the gate and actual combinational circuits here. Till then, please watch the previous video and this video a couple of times so that you really understand it before we go into the next step. It's an important concept, so take your time and learn it properly. Thank you so much. See you next time.